Hey, today we are going to learn an integration technique. It's a pretty big one. It's going to be one of your most powerful tools, so it's pretty important. It's called substitution, and it deals with a lot of product rules. It does not by any means comprehensively deal with product and quotient situations, but it knocks out a lot of them. So the game plan is this. I'll write a list first and then we'll walk through it and explain it. So you're going to pick a part of the integrand for your u to be called u. Then you're going to find du dx or du dt, whatever it's in terms of. You're going to take the derivative of that part. Then you are going to separate your x's and your u's and adjust each side of the equation. And then you are going to substitute and integrate, and then you're going to substitute back in. All right, I know that doesn't make sense yet, but we'll walk through a problem with it so that it does. So here we go. Here's our example. We're going to integrate 3x squared x cubed minus 3 squared dx. Okay. So again, just to review, if you got this problem cold, you would look at it and you'd say, hey, this is a product of two things, so I actually can't integrate it. And your only course of action would be to square this term out and then distribute in the 3x squared and do it term by term, which you definitely could do. And on some level, sometimes it's faster to do it that way. But as soon as this power ends up being like a 5, then you don't want to multiply this out anymore. Okay, so that's kind of the thought process going into the problem. Now let's walk through the steps. So the first thing you're going to do is pick a part of the integrand for u. And this is often the trickiest part. I'm going to give you some hints as to which part to pick down the road a little. Well, maybe I'll outline them as we go. So often, now these are suggestions and oftens. They're not rules, okay? So often u wants to be the higher power. Now the reason is because you're going to take the derivative of it and drop the power. So there's kind of two parts to this problem. There's this piece and there's this piece. And yeah, there's a squared on there, but that's kind of like maybe the format of the function and not like all the stuff in it. And so I'm going to pick in this, I'm going to say let u equal this inside stuff with the higher power. See how this guy has a squared on it and this guy has a cubed? Now once you see how this works, you'll probably understand how to pick your u better. So let's just keep going. U is going to be that piece. And then the second thing is you're going to take the derivative. You're going to find du dx. So du dx is going to be 3x squared minus 0. Okay, that's our derivative. Now, I want you to remember this notation. This is why I made such a big deal about this notation before. This notation is a rate of change. And if you remember back when we were in terms of x and y, we had a function here, and we were talking about the tangent line, and we were talking about that this is the dy part and this is the dx. It's actually the slope of that secant line, and then as you slide those points together, it becomes the derivative. But what I want you to understand is that the dy dx part of these things is actually a measurable distance. Okay, and so when we put them as a fraction, dy dx, it is actually a fraction. This is some number over some number. So algebraically, we can pull these apart. It's not like a one-piece notation that always goes together. We can pull them apart, which is what we're going to do in step 3. We're going to separate our x's and our u's by basically clearing your fractions. You're going to multiply both sides by dx, and that's going to cancel this guy, and then I've got du equals 3x squared dx. So all my u's are in one side and all my x's are in the other, and there's no mix and match. So there's no u's on the right, there's no x's on the left. That's the idea. And then you're going to adjust each side of the equation to match your problem. So let's look at this. We've got, I'm going to do this in color. You've got your u part. The idea is I want to account for every part of this integrand. So your u part is this piece here. Okay, that's this x cubed minus 3. Now your du, sorry, here, your du has to account for the rest of the problem. So I've got a 3x squared and a dx, and up here I've got a 3x squared and a dx. That's how you know you're done. Okay, this is a simpler problem where the du ended up just falling out the rest of the problem. But sometimes you have to adjust this side of the equation to account for all the things that you're seeing up here. Okay, and now we're going to substitute, and you have to substitute for everything that's in pink and green. Okay, so we've got the integral. The green is all going to become du, okay, because this piece becomes du, and the pink is going to become u. Now, what have I not accounted for? Well, there's still this squared here, so that actually stays in the problem because that was not part of my substitution. So everything in pink and green gets substituted out and everything else stays, like the form of the problem stays. So if there was a root in there, the root would stay, okay? If there was a log in there, the log would probably stay. Right? And what that does is it creates an integral now that's just a simple power rule. And now we can integrate that. So that's going to be, that's step 4, substitute and integrate. So I substitute in, and now I go, okay, this is x cubed over 3 plus c. Okay, the integral and the du go away when I do that. And then step 5 is substitute back in. So now instead of u, I want to substitute in what does u equal? U is x cubed minus 3, and everything else stays. So this is my answer right here. Okay? So now let's look back. Now that you kind of see what's happening, look back at this rule here. U wants to be the higher power. Why? Because I'm going to take the derivative of it, and I want the du to be the rest of the problem. So if I let my u be the higher power, then the derivative is going to take care of all the lower powers. That's kind of the idea. Now, the tricky part about these problems is deciding what the u is going to be. That can be tricky, and sometimes I pick u to be something and it doesn't work. And so you have to back up and try something else. There is a little bit of guessing involved, okay? But there's smart guesses along the way that we'll try to point out. So try one of these simple examples. Let's do 5.31. Okay, so stop the video, try one of these, and we'll go on to something a little bit more challenging. All right, next example. Okay, now we're in terms of t, so just use the correct variables as you go. And again, notice we've got a quotient, okay, which is a problem. We've got quotients and powers, all problems. So that's how I know I can't use my simple power techniques. I need to do something else, and u substitution is the only thing we have. So the first step is to figure out what u is going to be. And so you've got kind of some options. Typically, u does not include any powers. That is not a universal rule, but typically, okay? So let's write that down. Typically, we don't include powers. Like overall powers. I mean like these kind of powers, like where it's stuffed to a big power in the u pick. Okay, and here's why. I'm going to do this problem actually a couple of wrong ways and kind of show you what happens. Okay, so let's say, for example, we wanted to let u be sine squared t. So I decided to include that power in what u equals. Well, then du is now a chain rule. So this is going to be outside the derivative of the outside function evaluated at the inside function times the derivative of the inside function. Okay, now look at what happens. Yes, you did a great job in substituting this guy, okay? But the only thing I have left now for my du part is the cosine and the dt. But look at what I have over here. I've got a cosine and a sine and a 2, which is way more than I have up here. So that taking the derivative of that power creates a chain rule and often creates way more terms than I want. Okay, now it might be that the green top part here has all this stuff in it, in which case that is the correct choice. Okay, but often it doesn't. So that's kind of that wrong move, and so I would do that and I'd say, oh, let's see, okay, that's too much, so let's do a different pick. So what if I said, okay, what if u is cosine t? Oh my gosh. Then the derivative is sine t. All right, well, maybe that's okay. I split this up. Multiply through by dt. So I'm going to go sine t dt. So here's the problem. First of all, the sine in the original function is squared, and this one isn't squared. And if I multiply by a sine t to create that squared on the right, I have to do it on the left also, and then I'm mixing t's and u's. So that's an illegal move. Okay, so let's see. The other problem is that this du ends up being part of a denominator. And I don't know if you noticed, but whenever we have an integral, the dt, du, dx, whatever's out here is always on ground level. It's never under a fraction. So if you ever get a situation where your du is going to end up being part of the denominator, that's bad. Okay, so this leads me to kind of my other, we'll outline these all together at the end, but my other trick. U should be the higher power. U is often the denominator. Again, without the power. So in this case, this will show that suggestion clearly. Both of those situations didn't work. So let's let u equal sine t without the squared. Then I've got du dx, or du dt is cosine. And now when I multiply by the dt, the du is going to be cosine t dt. Now let's evaluate if I did it well. So sine is taken care of there. The squared will come through. And the du is going to take care of the cosine and the dt. So everything's taken care of except that sign on the denominator, and powers are okay. So what happens here? I've got the integral of, downstairs I've got a u, but it's squared because this squared is going to be a squared on your u. And then all of this upstairs green gets taken care of with du. So you can write it that way, or you can write it this way if you like this better. They're both the same. Okay. And then we integrate. So this is going to be, I'm going to write this as u to the negative 2. So it's going to be u to the negative 1 over negative 1 plus c. And then after you integrate, you are going to substitute back in. U, we said, was sine t. So this is going to be sine t to the negative 1. And I'm just going to throw that negative 1 power on the bottom. So this is going to be negative 1 over sine t plus c. Okay. All right, why don't you try one like this? Example 5.32. Walk through that one. Hey, if you're not walking through these extra examples that I give you, you're kind of missing half of what would be our class. You know, like if for those of you who've had me before, I always do a problem and then have you try one. You're missing that, so you're actually getting half as much practice. So you've got to do this, otherwise the jumps that I'm making in my lecture are too big. So you've got to try these to have that incremental move as we go. All right, next problem. X. Okay. All right, now what are we going to do? We said that often u is the denominator, so I'm thinking that direction. Okay. We also said that often we don't put powers on u. So my inclination is to say u equals x minus 1, the stuff under the root. Now again, if u is the whole square root x minus 1, look what happens to do u dx. We get a chain rule. Yeah? Times derivative of the inside, which is 1. So I get this whole extra term right here that I don't have in the problem. So that is what picking your u too big, so to speak, creates chain rules, and that is challenging. So I'm going to let u be x minus 1. We'll see if it works. And then du dx is going to be 1. And now I'm going to multiply through by the dx. And du equals 1 dx. Okay, let's see what we've got going on here. The du is a straight substitution for the dx, and the u is a substitution for this x minus 1. So I've almost got it all taken care of, but I haven't accounted for this yet. So if I was to substitute in at this point, it would look like this x is not accounted for. I've got the square root of u downstairs and a du, okay? And this mix and match of x's and du's is black magic. This is not allowed, okay? So I have to compensate for this. And one trick that sometimes happens is you can go up here, and if you don't have too many variables running around, you can actually take this down here and solve it for x. So if I add the 1 over, I get that u plus 1 equals x. And I can take that is a u function, and substitute it in right there. Again, the goal is just to get this whole integral in terms of u's, no x's. And once you do that, you're good to go. Okay? Now, the question is, can you integrate this? It may still be undoable. But I think back to like our original tricks with quotients, and when there's only one term downstairs, what we did in previous sections is we broke it up. Remember that trick? Whoops, that's a u. Like this. So that still applies, and I think I might be able to get to a doable integral by doing this. This is u to the 1/2 if I reduce, and u to the negative 1/2. Okay, and now I think I can integrate term by term. So this is going to be u to the 3/2 divided by 3/2, and u to the 1/2 divided by 1/2 plus c. So this is going to be 2/3 u to the 3/2, 2 u to the 1/2, and then I substitute back in for the u, and my u value was x minus 1. So the idea is I'm taking out the complicated additions in this problem and substituting something simple in so I can integrate with my simple techniques and then go back to the complicated. That's the idea. Okay. I'm just looking at this. Oh, I simplified this. I was looking at my notes and trying to figure out what I did. I simplified this. I factored out, if you factor out an x, you can factor out a 2 and an x minus 1 to the 1/2 if you want out of these guys. Probably not super necessary, but let's just look at that if you want to do that. Again, the trick with these powers, remember, is factor out the lowest power. That's why I'm choosing the 1/2. And that ends up giving me a 1/3 in here, and it changes this to a 1 power, and then I factored everything out of this term, which is a 1. Alright, so then the stuff in here, I've got my c tacked on here still. The stuff in here simplifies to 1/3 x, and if I distribute this in and add the 1, I get 2/3 plus c. So that's fine. This would probably be fine for me too, either one, but some of you guys like to simplify quite a bit, so I wanted to show you that. All right, let's do one more. The key to these is practice. Let's talk about what happens when we put numbers on our integrand. So now this is a definite integral from 0 to 1. So this is actually quite a bit like our first example, where I've just got two polynomials multiplied. So my trick here is to let u be the higher power part. Again, I don't want to include that 5th power because I'll create a chain rule that I don't want. And so du dx is going to be 6x squared. Out, multiply through by dx on both sides. Now, here's a little adjustment that we haven't had to make. Let's do our comparison. Make sure we account for everything. This is this part, okay? The 5 will carry through, that's fine. But look at what I have. The du is gonna, I want it to compensate for a x squared and a dx. That's this and this. But I don't have a 6 in my original problem, so I actually need to get this out of here. And you can do that, that's legal. The way you do it is you divide by 6 or multiply by 1/6, however you feel comfortable doing that math, okay? The numbers can be on any side. So this ends up being 1/6 du, and now I've got x squared dx. So the idea is that you're matching the right-hand side of this equation to your original function. And then whatever the left-hand side is what you're gonna substitute in. So what we've got is we've got the u to the 5th, okay, that's the pink part. And then the green part gets substituted in for 1/6 du. This guy is that whatever's on the left is substituting for everything on the right. Okay, and our properties of integrals say that this 1/6 can pull out in front. Now, I don't want to get too far before I deal with those numbers. I want to come back to that. But this is what we're setting ourselves up for, okay? All right, so again, the thing I want you to see from this example is that you can take your du function and you can multiply through by any kind of numbers. You can add numbers to both sides, you can divide by numbers or multiply by numbers on both sides. As long as you don't put an x on the u side, the numbers don't matter. You can do anything you want. Okay, now what do we do about these numbers? These values are x values. And what we're doing is we are doing a problem in terms of u. So these numbers actually need to be substituted out as well. So what I do is I take each one individually. When x equals 0, what does u equal? Well, I'm going to use this formula to figure that out. I'm going to say u equals 1 plus 2 times 0 cubed. Okay, and so I get u equals 1. So when x is 0, u is 1. That means that my bottom integrand is going to change from 0 to 1. And then what happens when x is 1? Well, u equals 1 plus 2 times 1 cubed. So this is going to be 2 plus 1 is 3. So when x is 1, that's my top integrand, u is going to be 3. Okay, so when you've got numbers, you've got an extra little step there to change those numbers on the integrand out. Now we do our integration. The 1/6 comes along for the ride. The u increases in power, divide by the same power. Now, because there's numbers here, I don't need a plus c, just like in the previous section, but I'm going to say, yeah, I'm going to evaluate from 1 to 3. And the cool thing about this, because I put everything in terms of u, I don't actually have to substitute back in for x because everything's in terms of u. So I can just go ahead and plug in. So 3 to the 6th over 36 minus 1 to the 6th over 36. And I think that ends up being 182 over 9. And that's your answer. Okay. So again, recap, when there's numbers here, you don't have to substitute back in for x after you integrate. Just plug in your new numbers and you're done. All right, try one of these. This is, I want you to do 5.29, the check your understanding problem. Okay. I think I've got one more that I want to show you. So again, this is a definite integral. We've got numbers there. This is another trick I want you to know, or suggestion for how to pick your u value. And the hint is, if you have exponents with functions, make u equal to the exponent. Okay, so that's what's going to happen in this one. This is my exponent right there. So I'm going to have u equal 4x squared plus 3. And also notice that the x terms I have down here are a lower power than they are up here. So it's kind of that power rule again. Let x be your higher power because the du is going to lower the power. Now, if I let u be the whole e to the all the stuff, again, I'm creating a chain rule, which is going to mess things up for me, usually. Okay, sometimes I want to mess things up, but the derivative of this is way too much stuff. This is the derivative, and it gives me an extra e term and an 8x, and that's too much. Okay, all I need is an x term. That's the only other thing I have to get rid of. So that's what makes this not work. And we go over here, let's make this, that's our derivative's 8x. We multiply through by dx. And let's compare. I've got this pink is taking care of that. Okay, the e is fine. The e is like a number, so you don't have to compensate for that. There's no x's involved there. So I've taken care of that. My du so far is taking care of my x term and my dx term, but I've got too much. Okay, I've got an 8 here and I don't have an 8 up here. So I need to get the 8 onto the other side. So that's that trick again. So this is going to be 1/8 du equals x dx. And now I'm ready. The idea is that the right-hand side is your original, and the left-hand side is what you're substituting in. That's the idea. You're splitting this left and right. So yes, this x dx compensates for what I have here, and this is what's going into my my substitution there. And then what do I have in the pink? I've got an e to the u. Again, these the 1/8 can come out front because it's a power, and I'm left with e to the u du, which I definitely know how to integrate. Now let's talk about our parameters here. When x equals 1, okay, I'm looking at the numbers here. I'm going to use this formula always, and I'm going to plug in. So I get u is 4, 5, 6, 7. So this becomes a 7 up top. And then when x equals 0, u is going to be 0 squared plus 3. I don't need to see this work, by the way. I'm just writing it down so that people are clear in the notes. So when x is 0, I get a 3. So my new numbers that I'm integrating between are 3 and 7. Now I'm going to actually integrate. The integral of e to the u is e to the u, and I'm evaluating from 3 to 7. So this is going to be 1/8 e to the 7th minus 1/8 e to the 3rd. Okay, and then, I don't know, I probably would factor that out, maybe something like that. What? E to the 3rd, like that. That's your answer. That's a number. Okay, yeah, I mean, you could get a decimal if you want. All right, so try an exponent problem, 5.30, the check your understanding. Okay, and then I just wanted to outline all of our tricks, our ideas for what u equals. Okay, here they are. The first is pick your highest power. If you have a choice, if there's two parts that have two different powers, pick your highest power. The other is pick the inside of a root or a power, like when you have a bunch of stuff to a power, pick the inside part. Okay. Our other idea is pick the exponent. If you've got like 2 to a bunch of stuff or e to a bunch of stuff, pick this as your u value and leave the power. And our last idea is pick the denominator if you have a choice between top and bottom. Okay, so those are ideas. Now again, ideas, if you try one and it doesn't work, then try something else. Sometimes there are problems that don't kind of follow the rules, and just be patient with these and be okay with starting a problem over if it doesn't work. Okay, I will see you in class for questions.